Good afternoon. My name is Noel Davies, and I have been working with agricultural scientists at UTAS for over 30 years. Did a quick count. In the last few years alone, there's been over 40 members of staff and students that have utilised the organic mass spec facility, and I think if I go back through the lifetime of the facility, we're up into well over 100 people from this building have used this facility down there. So there is very widespread applications for mass spectrometry and the chromatography that we use in this facility in your area. I myself am an agricultural scientist in my undergraduate years. I'm going to talk a little bit about sugars as an example, but just before I do that, I just want to give you a background on the sorts of applications that we typically apply organic mass spectrometry to in the CSL. All the ones in bold here, the top six are highly relevant to agricultural scientists, perhaps the bottom four not so relevant. But these are the bread and butter of what we do down there, and we're basically driven by these particular applications. And what we have is state-of-the-art GC-MS, direct probe MS, UPLC-MS, which is ultra-performance liquid chromatography mass spectrometry, and tandem mass spectrometry, MSMS. So we've got instruments purchased in 2010 and 2011 that cover these areas. What do we do with mass spec? We can either do a targeted approach. So many of you come to me saying, I need to look to measure or identify a particular compound in a particular matrix. So we can do this targeted approach looking for specific known structures. So we can look up the spectra, we can look up their molecular weights. We can buy standards in many cases to help us sort this out. We can do a non-targeted approach. You can come to me with a sample and say, what is in my sample? And we try and tell you as much as we can about the chemistry of your sample. And the third area that we've gotten into recently is metabolomics, which is the ability to find chemical markers between different treatments or different disease states or different genotypes. So you're basically taking two sets of samples and looking in a non-targeted way for chemical markers that will show up those two states. But really, in the time we've got available, I just want to use the example of sugars to illustrate how the technique works. You'll remember from your undergraduate years, sugars are basically involved as carbon, hydrogen and oxygen joined together in these different ring formations. So fructose, glucose, sucrose are probably the main three sugars in most plant systems, but there are in fact hundreds of sugars, or not hundreds, scores of sugars. So you end up with trisaccharides like this, where you get 3 sugars joined together, or tetrasaccharides, 4 sugars joined together. We also have the sugar alcohols like this, where we just have hydroxyl groups around a ring. So the diversity is quite big, and what I've marked here are the ones in red, the ones that we've actually looked at directly down in the CSL. But there's a huge range of monosaccharides, a huge range of disaccharides, and a significant range of sugar alcohols. So it can be quite problematic even identifying these sugars unequivocally in the first place, which we'll see in a minute. The problem with classical determination of sugars is that they have no UV, or almost no UV vis absorbance. So if you run them on an HPLC column and try and detect them, you're going to get a flat line because there's just no absorbance on that detector. So they're typically used non-specific detectors like refractive index or evaporative light scattering detectors, which are fine, but they're not particularly sensitive. And the bottom line there is that you must resolve every single sugar from every other single sugar, because you've got a non-specific method of detecting them. If you've got a mass spectrometer on the end, and if your sugars are of different molecular weights, then it doesn't matter if two of your sugars are essentially coming out at the same point in time. So we're turning a non-specific method into a very specific method. As I said, these techniques are relatively insensitive and require total separation. So this is our LC-MS, UPLC-MS down in CSL. The UPLC is this device here. The mass spec is all of this, and the UV detector is a little bit up here. And we use the technique called electrospray ionisation to get our sugars into a form that we can actually see them inside the mass spectrometer. And we're looking at negatively charged ions. UPLC is, most of you are familiar with HPLC. UPLC is essentially the same, uses an aqueous organic mobile phases. The main difference is that the particle size is 1.7 microns, and that gives us much sharper peaks and much more rapid analysis time. So you guys win out both in terms of the cost of the analysis and in terms of the separation that's achieved. So I'm only charging a third as much now for the work that I do compared to what we used to do on the old HPLC, because it takes about a third of the amount of time. You need pressures up to about 15,000 psi to drive this, so they're very specialised pumps. And many of these analyses are completed in 5 or 6 minutes, and then we can recycle and get on to the next one. In the old days, we'd be looking at typically 20, 25 minutes. The electrospray technique itself won the Nobel Prize for John Fenn, who invented it. Simply the solvent comes out of the end of the capillary. There's a high voltage applied to the end of that capillary and a gas to help nebulise it. And the beauty of it is that it doesn't matter if you've already got an ion in solution or if the molecule in solution is a neutral. As the solvent evaporates, the electrostatic charge that builds up on that droplet is so huge that it imparts charge to those ions. It either protonates or deprotonates the compounds that are neutral in solution. So the evaporating droplet ultimately becomes a series of individual ions. They're sucked into the mass spectrometer, and bingo, we get our sugar, which is a neutral, turning into an ion, which we can then look at inside the mass spec. So typically we see protonated species with perhaps 2 protons, 3 protons, or sodium, or we may lose a proton, we may lose 2 protons and pick up a sodium. All sorts of combinations occur, but typically we're looking at this one or this one. So we look at sucrose, we just get a beautiful M-1 ion, very, very clean, simple spectrum. And we look at it by either looking at a single ion, which gives us nice, maximises our sensitivity and also gives us very smooth chromatographic peaks. We also have the technique of MS-MS, or tandem mass spectrometry, to give us enhanced specificity in the detection. So we can look at an example is we can look at an ion mass 221 that was derived from a mass of 341. That's a very, very specific request of the detector, and there's very few things that are going to fulfil that. So you basically have a flat baseline, and only things that fulfil that request are going to produce a peak. Here's a couple of MS-MS spectra of 2 different disaccharides, so they have the same weight, but very, very different spectra, and we can discriminate them on the basis of these spectra. This is some work that we did with allyl looking at sugars in eucalypts, and some of them are quite straightforward: fructose, glucose, sucrose, raffinose and stachyose we expected and were quite straightforward to identify. We're able to get standards for these. Gentiobiose and galactanol caused us a little bit more problems in terms of identifying them. We had to go through all of the available sugars that are in these that are out there, and then we had to try and find some standards to match retention times. Basically, to make sure you've got the right sugar, you need to prove that it dilutes at the same point in time and that it has the same MS-MS spectrum. And we still get some levels of ambiguity. But you can see if you're just after fructose, sucrose and glucose, inside 2.5 minutes, that analysis is finished. We then need about 2 minutes to recycle, ready for the next analysis. So 4.5 minutes is the cycle time for that simple sugar analysis. There are a couple of caveats. The mass spec is it's an instrument that requires regular calibration, not like a UV detector where the response is proportional to the concentration. You must calibrate very regularly. We get very non-linear standard curves, so we run QCs all of the time, and we often find the use of an internal standard improves our precision. So you can see here the shape of these standard. Some people purists might say, well, you can't use that because it's not linear, but our correlation coefficients are typically 3 nines or 4 nines. We don't have any problem using these standard curves. This non-linearity relates to formation of dimers and sodium adducts and so forth as the concentration rises. We get some very nice correlation coefficients you can see here across all these sugars from eucalypts, and very nice quality control samples. 750 was the one we put in. These are the numbers we read back, and these are the standard deviations. So we're more than happy with this as a routine method for analysing sugars. Sensitivity looks good here, so we're down to parts per billion for sucrose and fructose, but this is for 1 microlitre. We can increase that by a factor of 40 simply by matching our solvent that the sample is in to the mobile phase that the UPLC is running. And these limits, I mean, we did an assay last night where the detection limit was 3 parts per trillion for another compound. So mass specs are intrinsically sensitive devices. So we're often down in very low parts per billion and in the parts per trillion range in terms of analysing these compounds. As I said, retention time is one of the main methods of identifying sugars. The MS-MS spectra are they're like a fingerprint, but unlike the old electron ionisation spectra where there are hundreds of thousands of available reference spectra, these are only just being started to be developed. So there are libraries starting to be developed of spectra of individual pure compounds, but they're not all compounds are represented. It can be quite challenging to even identify the compound that you've got, and sometimes ambiguity to that is still possible. And that's all I'm going to say. The work was really belonged to Alida Isles and Joe Jones and Caroline Clay, who did some work on sugars in grapevines. And thank you.